terminal value also satisfies for certain conditions. So the difference between this and this is going to be half this one, right? And this, you remember, theta minus theta 0 over the distribution. So when you take in a sound like that, we need to multiply this by 2 in order to put that in. So usually you do this type of normalization in order to get this distribution. And when you think about also the F distribution in linear equation, it's basically the relative change in output, right? But you need to normalize it in the case of freedom. But the data is just the way the output is when you have that.
Why not multiply by any other number other than 2?
Why don't multiply by any other number?
Other than 2. Or
that's not what I was trying to explain here. So here this goes to 0. And so here we have 2 times n of theta as 0. It's this. This is the variance. And then you have this. Now we know from the previous slide that conversion normal. So this sum will convert to a chi-square distribution. So we are done. We already know that 2 is our third number. So maybe in other contexts it will be a different number, but it doesn't just arise arbitrarily. So it's based on the fact that the right-hand side is a target that we have. So if we are testing the same restrictions, now we use the wall test. Then basically what we do is we define the wall test as this sandwich estimator, right? So we evaluate the restriction on the MLE, and then we take the asymptotic variance in the middle, and then this follows a chi-square distribution. Now, the restrictions are known. The maximum likely estimator is already given, so you can evaluate this, right? And this. So the only thing that you're wondering how to evaluate is what is in the middle. Now, how do you get what is in the middle? Well, you use this property, saying that if you write this, you can basically say that this is equal to this. Now I need somebody to tell me why this is equal to this. Where is that coming from? Of the MLE? Yes. So it's coming from the asymptotic distribution of the MLE because we know this. We know this is the asymptotic. So this is the asymptotic variance of the MLE, right? But why can we say that this is equal to this sandwich thing? Basically, what I'm asking you is, why is it the case that so usually what we, yes, it is the delta, right? So basically, it's based on the same type of approximation. It is the delta. So usually what you know is that if you are looking at the variance of, let's say, R times theta hat, R is just a constant or a matrix, right? It's going to be, let's put it like this. It's going to be R, the variance of theta hat, in a matrix form. In the scalar, so this is the matrix form, right? Or the vector form. But in the scalar form, I'm sure you all know that if you write it like this is R squared, right? So the variance of R theta hat is R squared. Wait, but if you have a vector, then it becomes like this because you always need those matrices to match. Now this is with linear combinations. What happens when we have non-linear relationships, right? So we have another result for that. So we basically say that if the variance of a function of theta is what we want to get, that basically we can just take the partial derivative. We take that variance of theta hat and then the partial derivative. and this is the delta method. And that is useful when you're trying to test for nonlinear relationship, right? So if the null hypothesis is a set of nonlinear conditions, then that's what you have. So you can compute the variance of a function of your initial parameter of interest, or a function of your estimate of interest, whether that function is linear or not. If it is linear, it's obvious, it's obvious. If it's non-linear, then just take the factor. Yes?
Remind me of the last equality construct that that's kind of analogy before.
Excellent. So this last equality comes from the fact that the asymptotic distribution of the ML estimator is the inverse of the information matrix. And so the asymptotic variance is just this.
So the regularity equation is something like that?
Exactly. I think I put it somewhere here.
Oh.
Right? So this means it's normally distributed. This is the mean, and this is the variance. Right? So the variance of the ML is the inverse of the information matrix. And that's what it is. So that's the way that you can use to test for the Wald distribution, for the null hypothesis using the Wald statistic. The last one is the Lagrange multiplier. I wrote a word that is Lagrange multiplier. Same restriction, but now you have the score on both sides. Now the score is evaluated at a constraint likelihood function, at the constraint maximum likelihood estimator. And it also has the chi-square distribution. Now, if you remember, if you are using the first order conditions, then the score evaluated at the MLE is 0. But this is the score evaluated at the constraint MLE, so it's not necessarily 0. And that's why it's called Lagrange multiplier, because as soon as you have a constraint, you usually use the Lagrange approach in order to derive the maximum. Questions? Now, since these three tests are equivalent, how do you choose between them? So what's the difference between them? They are all asymptotically equivalent to a chi-square distribution. Now, I want you to notice something here is that regardless of your MLE, you are not using the MLE in this test. You are only using the constraint MLE, right? You are only using theta t. There is no way theta hat is appearing in this test. Now, if you are using the word, you are not using the constraint, you are only using the MLE. So there is no way the constraint MLE is appearing in this test. And if you are using the likelihood ratio test, then you are using both the constraint and the unconstrained. So in some cases, it might be difficult for you to get the constraint because the constraint is so sophisticated that you can't get it. And so in that case, you will be using the Wald statistics, right? But in other cases, the MLE itself is complicated, but the constraint MLE is easy to get. And so you use the Lagrange multiplier test. But in cases where you can easily get both, then you can use either of those three tests, all right? So in finite sample, so if the sample size is not large enough, those three tests are not necessarily equivalent. They are only equivalent when you have a very large sample. And also that's supposed to also be a criteria for choosing one of them. Questions?
So in that example, can I create a situation where I end up making different, I end up with different conclusions based between.
So in finite sample, you do what?
Can I end up in a situation where after running those three tests, I get results that are like not similar? Not the same.
Yeah, it might happen in practice that if one of the tests you reject, and maybe the other test you fail to reject them all. But those are going to arise very in extreme cases.
And what am I supposed to do on that?
but it's also possible. For example, in the linear regression model, with finite sample, right, it's possible to show that the likelihood ratio test, we have the Lagrange multiplier, and then the point. So in finite sample, with the linear regression model, we always have this. And so these statistics always dominate this and always dominate this. And so for a non-hypothetical, and you know that you reject when either of this is bigger than the critical value, right? So for some cases, if the critical value is somewhere between these two, then you will not be able to reject this one. And so this is going to be the one that we can
With which sample size can we say that the sample is not finite?
What?
When can we say that the sample is not finite?
So that's a good question. So when can we say that the sample is large? Then somebody help answer that question. When do you have a large sample? When can you say that the sample is large? 30 observations. So who thinks that when we have more than 30 observations, the sample is large? Now you're backing off your... So it really depends on the context, right? It really depends on the context. So let's say, for example, you are using macroeconomic time series theory, right? So 30 observations means 30 years, right? So that's like a lot of years. So that's a lot of years. So that's kind of a large sample. So it's representative, it's large, it's macroeconomic data that appears every year. So we have 30 years of observation. Now let's say, for example, that your sample is the population of Benin. So you have household survey data, right? And then somebody extracts a sample of 30 households. And then he says that this is a large sample. Do you agree? So it really depends on the context, right? So in the case, for example, of household survey, 30 will not be enough. But in terms of sometimes, especially annual or biannual data, then it makes sense. In the case of censuses where you have observation every 10 years, that's even better, right? So 30 observations means 300 years.
Yes. Is there any rule behind that choice? Choice of that number? Is there any rule?
There is no formal rule. It's a common sense thing. But there is a way to see whether your sample is large. So what do we mean by large? It's a concept of convergence, right? So it's large when any additional observation doesn't significantly change the result. But if additional observation keep changing the result a lot, then you know that you're not converging it. So it's not large. So when we talk about large sample, it's really a convergence concept. We say that it's large because we want to be able to apply the law of large numbers centrally. So we want to say that something is asymptotically equivalent to someone else. By asymptotically equivalent, we mean that any additional data point doesn't significantly change. So sometimes you can use that figure to and it really depends on the context.
So if my sample for every country in Africa, I have a large sample.
So what do you mean by
Like 53 countries.
relative?
In that case, I can apply all
So
the large.
your unit of observation is country.
Yeah. And I can apply the property of
I think you can. complex is your model.
And I think we'll have to differentiate between having the observation that you talked about and likewise the scope. Because taking 50 countries, that is the scope you have. Each and every country may also have a sample size that you have.
Yes.
But there are models that actually can go even beyond issue of society. For instance, if you take issue of volatility matters, where you are arriving at about 1,000 data points, 2,000 data points, 4,000 data points for you to make analysis. But if you have less than even 100 or 200 or 3, now that one will not give you a robust result for you to pass recommendations. Thank you.
All right. So, questions before I move to. Yes.
Say that what is the last aspect of the process? So I would say that the central material has particular in the context of process management.
No. So I'm saying that the central issue is that if you take a sample average, which is large and with a sample that lies on, then the distribution is going to be normal. Now, what does it mean to be large and normal? Well, what you're saying is that the distribution doesn't change with its sample size at some point. So if you keep increasing the data or the number of observations, you don't really change anything in terms of your major results. Let's say I take a sample average, and then I want to see this, my target is the population average. Then at some point, with let's say 1,000 observations, the sample average is let's say 0.2. Then I add 500 more. So I have now 1,500 observations. And the sample average is 0.2001. Is that a big difference? No. In that case, you will say that, well, 1,000 is large enough. Because with that, I already have, I'm close enough to the target.
Let us assume that the sample is not large enough, and can we bring the word and the likelihood test using the asymptotical properties like normal asymptotical normal or the others? Because with those tests we are using the variance coming from the convergence.
Yeah, very good question. So, this test converts to a chi-square distribution, regardless of the original distribution of the data. Okay? And if I don't have the live sample, yes, I can still use this, provided that I have the distribution that's normal to begin with, for example. So, in the context of the linear regression model, where we assume that the error term is normal, yes, I can still use this test even if the sample is not small. But there are better tests to use in that situation, right? There's the T test, there's the F test, so you don't really need to use this, the likelihood ratio or the LM test. So in the context of linear regression analysis, if you assume normality, then you don't need to use this test, right? Because you already have the distribution which is normal, and so basically you can use all those other tests, like the T, the N. What's interesting is that those T and those F converge in distribution. The F, if you adjust the F, for example, with the second degree of freedom, is going to converge to a chi-square. The T distribution converges naturally into the Z. All right? Okay, so let's move to the limited dependent variable, which is an application, so where we are going to apply the maximum likelihood estimation. So what do we call limited dependent variables? So only defined as dependent variables whose range values are substantially restricted. So the values cannot range from, say, negative infinity to plus infinity. They are restricted in some way. For example, if the dependent variable of your model is binary, it only takes 0 and 1, so it's limited. So if it's a percentage, it only goes from 0 to 100, so it's also limited. It would be the number of times that something happens, right? So the number of times that somebody is arrested, the number of times that somebody shows up in the counter in the bank, and so those are limited, right? Because they don't take negative values and they don't take pure real numbers, so they have to be integers. And also you have like for a GPA, another example, it only range from 0 to 4 or from 0 to 4.3, things like that. So those are limited. So what do you do with that? Do you still apply the conventional linear regression analysis that you know? Or is it different, right? So the answer is that yes, it's different. You cannot just use your OLS like that. And I'm going to show you what happens if you use your OLS, your usual OLS in that case. So let's start with the binary choice model. So usually, if your dependent variable is only takes 2 possible values, right? For example, you want to predict the probability that somebody gets married, right? And that's only 2 possibilities, married or not married. Or the probability that the firm becomes formal. There's only 2 possibilities, formal or informal. There are many cases like that where your dependent variable of interest only take 2 possible values. Or you only want to focus on 2 possible values, right? It could be, there could exist many other alternatives, but you really focus on how to change from one to another. And so there are 3 popular approaches for that. You have the linear probability model, you have the probic model, and you have the logic model. So those are the 3 most popular approaches to deal with binary dependent variables. Now, for all these models, we are going to assume that you observe the choice of each individual. So it could be either 0 or 1. So for each individual, we know whether the person owns a home or not, or owns a car or not. Right? For each firm, we know whether the firm is formal or informal. And then we also observe the other characteristics of each individual. So for each firm, we know the size of the firm, we know the age of the firm, we know the location of the firm, right? So those are the vector of characteristics. And so that's going to be our basic assumption. So that's the data that we have. Now let's say that you start with, you say, well, I don't really care. I'm still going to use my OLS. If you do that, we say that you're using a linear probability model. That's how we call it. The linear probability model is just running on OLS regardless, even when yi is binary. It only takes 0 and 1. Now, because yi only takes 0 and 1, it's easy to compare the expected value, which is just this, right? The expected value of the right hand side is this. But the expected value in this case has different meaning. It's the probability that y takes the value 1, right? It's the probability of choosing the option 1. So the expected value is not the same as in a linear regression model where it basically just looks like this. But this is also the mean, the probability. And then you see why it has some consequence. The fact that the regression function is a probability. Now let's say that you apply the OS in this model, right? You say, well, I'm going to use the linear regression model. So there are some pros and cons. So it's easy to estimate because everybody likes OS, right? You just run any software reg, you get your input, right? And it's also easy to interpret because the coefficients of your regression are constant, and they are really what they really capture is the change in probability. So for example, if you have the probability of becoming formal or informal, and you're looking at education, the coefficient of education tells you what is the probability that you become farmer for one additional year of education, right? It really gives you the number that you want, and that's why this linear probability model is interesting. So, but there are also some cons. The con is that, well, the regression function turns out to be a probability. If it's a probability, then it has to satisfy the properties of a probability. First of all, it has to be fitted between 0 and 1. Turns out you cannot restrict this quantity between 0 and 1, right? Because you have no control on the x's. So this x can vary because it's a continuous, it can vary very large values, whereas this estimator is fixed. And so this whole thing can just go way above 1 or way below 1. And that doesn't make sense because this should be a probability. And that's the first issue in the linear probability model. Because the predicted values have to be probability, but you cannot control that. So there is nothing you can make in terms of saying, well, these are the predicted values, these are the predicted probabilities, because this predicted probability doesn't make sense. Now the second issue is that the linear probability model is systematically heteroscedastic. Why? Because if you compute the variance of the error term, this is what you have. The variance of the error is a function of the x. Now we know that if you have heteroscedasticity, then you should be careful about your significance test, right? The significance test, the t-tests that you use are based on the fact that the error terms are homoscedastic. So as soon as the error terms become heteroscedastic, then you should be careful about your t. Your t might not be meaningful, right? So if you're using your t, you might be lucky that it doesn't change much, but to be rigorous, you could, right? Because the error terms are heteroscedastic. And for a heteroscedastic model, we need to address that in order to be able to do rigorous uses. And so those are the two critical issues with linear probability model. There is another issue that's even worse. It's the fact that suppose that you have a treatment effect model. The dependent variable is the probability, and then one of your key right-hand side variables is treatment, whether the person is treated or not. I want to see the impact of the treatment of the probability of getting something. Right? Let's say there is a reform where maybe you give cash transfer or something like that to household, and you want to see the probability that those households send the kid to school. Right? If you use a linear probability model, it will just look like this. Right? The left-hand side, 1 if you send your kid to school, and 0 after 1. And one of the key explanatory variable will be a dummy of whether you got the transfer or not. So that's like the treatment of impact evaluation. The worst thing is that if you use the linear probability model in that cases, it is possible that the effect that you're looking at is going to be biased, and it can actually even assume the wrong sign. Right? It could be negative, although the truth is positive. If you're using the linear probability model. And that has been proven recently by a paper by Hubert, Dong and Yang, 2012. And so you have to be careful when you are using the linear probability model. To be safe, don't use a linear probability model. Use probit or probit. Why? I will tell you that in the second one. Right? So first thing is that you want your probability to fit within 0 and 1. And so you want the probability of success or probability of getting house or sending to school to be a function that fits between 0 and 1. That's the first issue. So you want to be able to meaningfully interpret the predicted probability of the model. Right? And for that reason, you need to make sure that these predicted probabilities make sense. And so if you choose, so the problem comes of choosing the correct J, but there are many candidates for this. The most popular candidates are normality and that's how profit and limited models arise.